To start our series of lectures about the end point of stellar evolution and supernovae, I start with the very basics of stellar evolution theory, which lead to the collapse of the massive stars and also the starts the explosion. So first of all, of course, we need to ask ourselves what is the star? What is a star, and what are we going to talk about? So let's say a star is something bounded by self-gravity, so what we call star here. And then we can also say star is something radiating energy which was supplied by the internal energy source or by in itself. So apparently, so of course, sun is probably we can call. Sun is a star because it's bounded by self-gravity. It's shining by its internal energy, which is basically now provided by the hydrogen fusion. And then how about Earth? Earth is not radiating its energy by supplied by itself, and it's basically reflecting the light from the sun. So probably we don't call it star. And say how about comets? It's basically the same. It's not radiating energy by itself, and it's shining. It's by reflecting the light from the sun. And then how about supernovae? Supernovae have energy from itself, but it's not object bounded by the self-gravity. So we don't call supernova as a star. So suppose there's an object bounded by self-gravity, and then if this object is radiating energy by itself, then what happens? So because these stars are releasing their internal energy, and then it's losing the energy which is supporting itself at one time, and then as it loses the energy, then this thing needs to change because its energy is losing, and the internal configuration needs to be changed as it radiates, loses their internal energy. And that leads to the evolution of the stars, and that's what we are going to discuss in this lecture. So this is example. So let's say this is the temperature and luminosity of some star cluster which has the same age. So this is the youngest young star cluster, and this is kind of middle aged, and this is kind of old star cluster. And all the stars has the same age in each panel, and this is younger. And as you can see, very young stars, collection of young stars, it has just one sequence, and that's called main sequence. And as it evolves, this upper part of the stars will go to the less high lower temperature, and then in the end many stars evolve to this lower temperature side, and we see this kind of change in the stars as it gets older. And of course the purpose of stellar evolution theory is to explain this kind of change with time happening to stars. And at first in this lecture, I want to overview the basic equations in stellar evolution theory, and then we move on to the equation of states, which are also important keys to understand the basic stellar evolution theory. So we don't have much time in this lecture, so I will make many simplified arguments to derive the equations. And of course, for the full details, I suggest you to go through some textbook and so on, but I will give you some overview. And I will here assume very simple stellar evolution structure, and we assume just spherical symmetric star, and then I also assume here the star is hydrostatic, and under these assumptions we will see what's the basic equations in the stellar evolution theory. The first important equation is, of course, conservation of mass. Mass should be conserved. So that means if there's something, if there's a volume and if there's a density, and then that should be, this equation needs to be hold to conserve the mass. And since we are assuming the spherical symmetry, that leads to this volume to be 4 pi r squared dr. So the change of mass should follow this equation. And if we integrate from the center, then we get this mass at certain radius, and this increases with radius. This mass will increase as this radius. So this can be used. Mass can be used as a coordinate instead of radius, and that is often used to describe the stellar evolution theory. So I will mostly use the mass as the coordinate system. So this is partly because during the stellar evolution, radius can change dramatically and by many orders of magnitude, while mass will be mostly kept the same. Of course, mass can be changed during the evolution, but not that much. So in that sense, using mass as a coordinate will make make it easier to handle the equations. Please stop if you have any question at any time. And so that was the kind of very easy one. And then there's an equation of motion, which we can write in this way. So this is the acceleration term, and there should be a force governing this this system. So in this picture, so there's a mass shell, and suppose there's some small cube, some this kind of thing in some radius. And if you assume this is R or M, then there should be a gravity from in this system, which is written Fg, and then so this Fg should be just a gravity, and then there's of course there's a pressure on this side. On each side, there's a pressure in here. Let's say if this radius is R, then the pressure here is PR, and then so this pressure is coming. If we are looking in this, then pressure goes coming outwards, and then if we go slightly outward, then pressure here is coming into it, and the pressure is here is like this. And if we say this surface has the ds, then the pressure through this force which this object feels should be the second term. So that is so this force coming from this pressure gradient corresponds to this second and third term. Yeah, mass. I didn't say mass in this object should be dm is all rho times ds. That's the surface, and then this is dr. And if you do some easy mathematics, this small change in PR can be written in that way. Then that makes this second and third term to be like this. Just simply use this equation. Put this one to here, and then you can get this term, and that makes this original equation as this. So this gravity force was this one, so we put this. Then this second and third term just became this one, so that came here. Of course, you need to change ds, and then ds is written here. Then this can be simplified by removing dm, and just we are now assuming the hydrostatic equation. So this term, the term from the derivative by the time will be 0. So what we get in the end from equation of motion is this equation for which also governs the behavior of the internal structure of the stars. Then, as I said, this was written in radius coordinate, but we can also use the mass as a coordinate, and that will lead to this equation, which is basically these two equations is the same, but this is written in a mass coordinate instead of the radius. So this is the second equation, and then what we have next. So we also have radiation in the stars. This radiation will transfer in the star, and that needs to be taken into account. So here since we don't have much time, I will use very simple argument to derive the radiation transfer equation. Let's say there's some this kind of stuff here. If there's a radiation from inside, there's a radiation flux from this side, and then if there's some material here which has the density of rho, and then if the radiation passes through this place, some radiation will be absorbed, maybe sometimes emitted, but let's say this radiation will be taken by this material. And then as this radiation passes, then some original flux was lost due to the passing through this place. So how much amount will be lost how much is lost by this kind of process can be, let's say this. So the amount of the radiation energy taken by this object is probably, as if the density is higher here, then more radiation will be. You can imagine the more energy can be lost. And then, of course, if there's more energy, more flux is coming, then probably this object will take more radiation from the take more radiation. So we can imagine this. How much energy will be lost will be proportional to density and also the flux. There should be, of course, some constant to get the actual radiation taken from this material, and that's something called opacity. And if you think about how much momentum is gained by this object, then that will be just given by the momentum, the flux taken by this object divided by c. That's the momentum of the radiation taken by this object. So this object should have obtained the same amount of momentum from by this kind of by absorbing some radiation from inside. So that will give you the radiation pressure momentum difference. That will be the pressure given to this object from radiation. So this equation should be hold, and then again if you assume some small change, then this part will be like this. And then as we saw, this difference in the flux will be written in that way. So by equating, so using this relation, you can guess probably the difference in the radiation energy flux, radiation energy pressure will be written in this kind of way. And then since the radiation pressure is, we will see this later, but radiation pressure can be written in this way with temperature. So we can get the equation which is governing the radiation transfer. So I use very hand-waving argument to derive this equation because of the limitation in time. But this is you can derive this equation by by checking more. It's based on the radiation transfer equations. But anyway, this equation will be hold in the star. This was so then if you think about the whole surface of the sphere, then total energy going through a certain radius in a star will be written in this way. So in the end, the equation which is basically governing the change in the temperature in the star will be written in this way. And then this is in the radius coordinate. So if you use the mass coordinate, this equation will be written in this way. So to summarize, we have we saw these three equations so far, which is governing the inner structure of the stars. One is mass conservation. This was probably easy one. Then this was the equation of motion, and that governs the change in the pressure. And there's a radiation transport equation, which gives you a change in temperature in the star by the radiation pressure. And of course, we also have another equation which is about heat generation. So basically, so far I didn't include any like nuclear energy from the star. This flux you saw from inside the star is basically provided by the nuclear energy. So if there's the energy source, then that will give you some fluxes. Nuclear energy, about the nuclear synthesis will be covered by the lectures tomorrow. So I will just give you this equation, and that's the basic equations governing the. Yes.
But the principle, the sun, for instance, works in another way because there are convections. Will you discuss convection?
Yes, later. Yes. So convection. So that will be coming later. So yeah, I just said this radiation transport by the means for the flux, but there's another way to transport the energy, and that will be discussed later. So from these basic equations, we can already think about some properties of stars, which is timescale of the stellar evolution. So if there's some physical parameter, then if there's a rate of change of this, you can write the rate of change of this physical parameter, then you can derive the time scale for the physical processes to happen. And then we basically have these three equations. This is governing the motion, and this is the radiation energy transport inside the star, and this is nuclear energy generation in the star. And we can, for each equations, we can kind of think about the time scale for these changes to happen in the stars. So first one is this equation was from the equation of motion. So from this equation, you can think about the dynamical time scale. So the quantity which is basically determined by this the equation of motion is the radius. So let's say this is the radius of a star. And then what characterizes this radius is the velocity. And of course, we can make several ways of argument. But let's say this characteristic time scale for this change of the radius is something like escape velocity. Then, okay, maybe let me see. Maybe I made an even. Yeah. Okay. Sorry about that. It's. Yes, so this should be just there shouldn't be squared. Sorry about that. So okay, yes, that's yeah, and then this is correct.
This is correct.
Yes, so this. So then, yeah, then dynamical timescale will be R divided by this escape velocity, which will be this value. If you put, let's say, the solar value, then that may become the 1,000 second. So dynamical timescale of the star is, let's say, order of several thousands of seconds. And then from the second equation we had, which determines the thermal processes basically in stars, then that will give you some thermal time scale. So the time scale for stars to be adjusted itself from the some change in the thermal structure. So let's say in this case the total the gravitational energy of the star is written in, so internal energy which can be thermalized in the star is this the gravitational energy of the star, and then this will be radiated in the luminosity of the star. Then this thermal timescale will be written in this way. This timescale is also, this is basically the thermal timescale, and that's also called Kelvin-Helmholtz timescale. If we put the value from the sun, then this is what you basically get. So 10 to the 15 seconds, which is about 3 times 10 to the 7 years. So 30 million years. So that's the time for a sun to adjust itself in a thermal, the change in thermal conditions. So that's, which is much larger than the dynamical timescale we saw before. And then the final equation we had is this energy supply, and then total energy which can be taken from this nuclear energy generation is proportional to the mc squared. And of course you cannot get the energy from all the stars, so let's say there's some efficiency, but the total energy should be mc squared. And then that will be radiated in the luminosity at the surface. So we can again do the same exercise as this. So this will be the nuclear timescale. And again, we can put the number from the sun. And this epsilon, let's say typically 10 to the minus 3. Then you get like 5 times 10 to the 17 seconds, which is like 10 giga-year in the case of the sun. So these are basically 3 timescales which we can derive from the basic equations we saw so far, and that what basically dynamical timescale is the very extremely short, and then there's a thermal timescale, and then nuclear timescale is the largest timescale we have in this stellar system. And so what does it mean? So basically the lifetime of the star is governed by the nuclear timescale, which is the longest timescale we have. And so dynamical timescale is very short, but the thermal timescale is still this is very long. So if let's say we see many stars on the sky, but we cannot tell if it's in a thermal equilibrium or not by just observing them, because it takes 30 million years for the star to adjust itself for the thermal equilibrium. So the star may be still not thermally equilibrium. We cannot observe a star for 30 million years. So we cannot tell if just observing a star one time or in our lifetime if a star is somehow equilibrium or not. Yeah, but for the dynamical change on the star, this can be easily adjusted, and we can easily see if a star is dynamically stable or not. So that was about the timescales. And here is the convection we were talking about. So far, I assumed that only energy, the way energy is transferred in a star is through radiation transport. But that is not necessarily true, and sometimes star, the radiation cannot transport sufficient energy to adjust the star. And let's say we think, let's think about this. At some radius, there's some material in which has a density of ρ1 and pressure of P1. And suppose this part of the material in the star went up, and then it changes the density and pressure in it. So this went upward, and the original density in this radius was ρ2, and the pressure was P2 in this radius. And let's say this expansion was adiabatic, which we can usually safely. So we will see this in the exercise or seminar today. But if this process is adiabatic, we can relate the change in pressure and density by this motion in this way. So the change, this factor is called adiabatic index, and we can write the change in this sphere, this material, in this way. And then we can write the change in these changes in a different way. So this was pressure, and there was a pressure gradient here. So this change in the pressure will be written in this way, because there's a pressure gradient here. And then if we put this difference, if we put this here, then change this equation, and then we can derive change in the density of this material. And then the new density here will be, so originally this density was ρ1, and then the new density up here will be written by adding this change. So new density here will be ρe plus ρ1, which was the original density here, plus this change in the density which you expect from the adiabatic change. And then the density around this material, it can be written as the ρ1 plus change in the density, gradient of the density here. So we have the surrounding density and surrounding the material of the density of the material which came from the bottom to this radius. And let's imagine, so if this new density is new density here is higher than the surrounding density, then this material will just go back to the original position. So that basically means that this system is stable, because if the things went up, will just come down and then will be settled here. But then if the density here, new density here, is lower than the surrounding density, then this material basically keep going up, because you can imagine the buoyancy. This is unstable, and this thing just keep going up. So if this condition is satisfied, basically this structure, this material will be unstable, and then matters will just keep moving upwards. And that makes what we call convection. This is the motion of the material in the star, and that will also this material, of course, has some energy, and also some material, some energy inside. So this motion of the energy can transfer energy inside the star instead of, or in addition to the radiation pressure. And this is the condition we can write. If we put these equations here, then you can get the condition to be unstable like this. So what this convection does, so this convection is basically the motion of the material in the star. And so in what radius scale this can happen is basically this motion can happen in a pressure gradient, pressure change, typical pressure height. So if this kind of instability happens in the star, then this material will keep moving for a while and then stops at some time, and then that can be continued, and that leads to the mixing in a star, as well as the efficient energy transport in the stars. So this was some additional way to exchange material or energy in the star, which was not covered in the previous basic equations. So any questions, or is it okay? So then let's move on to the next important physical ingredients, which is the equation of state. And we here consider the gas pressure from ions and electrons, and then what is also very important in stars, electron degeneracy pressure, and that can be non-relativistic, or also there's relativistic. And of course there's a radiation in the star, and radiation pressure can also be very important in the star. We will overview these equation of states here, which is important to understand the stellar evolution theory. So we start from the yes. Oh yeah.
Can you somehow estimate the characteristic time scale of the convection?
Yes, but it's basically dynamical timescale, and that's very short. So if you are following the stellar evolution, this is just a motion of the material, and so that compared to the the other timescale in the star, it's basically very small. It just happens in a very short time scale. Let's say, yeah, I should say it's like sound speed time scale. It's just, you know, motion of the star. Yes. Yes. So this convection is very hard to, you know, quantify how much material will be actually moved in the star. Especially we are, you know, assuming the one-dimensional stellar evolution theory because it's the easiest way to handle the theory. But this is apparently not the one-dimensional motion. It should be, you know, multi-dimensional motion of the material. But we need to take this multi-dimensional motion into account in 1D stellar evolution theory, so that we need some simplified way to treat this convection in stellar evolution theory, which is very tough. And we, of course, we have some ways, but which is also uncertain, and that makes uncertainties in the stellar evolution theory. Okay. So yeah, ion gas pressure, and we are going to derive the equation of state, which relates like pressure, density, and temperature. And as a basic reminder, pressure can be written in this way if you have like a velocity or the momentum distribution given by NP, so that this, you know, you can, yeah, so you can imagine this. So this is the, you know, moment pressure given by some particles, and then this the number of the particles which has this momentum or this pressure is written in this way. And then, of course, we are living in a three-dimensional world, so some materials are going one way, an X way, and then some material are going to the Y direction, and the others are going to the Z direction. So, you know, we can, for very roughly speaking, if we think about the one plane, we are thinking of pressure. Then 1/3 of this all the material should go to give the pressure to one surface. So this is basically what the equation giving you the pressure, and yeah, you can get this kind of you know, equation, of course, by hand, and there's many textbooks will describe this relation. And for the ion pressure, the gas pressure, then if you this number density of the having some momentum will be the given by Maxwellian velocity distribution. So basically, you can get the pressure by putting this velocity distribution to that to here, and then you can integrate and get the relation between pressure and other variables. And in the end, what you get is this very simple equation. So ion pressure is proportional to the total number of ion, and then temperature, and also Boltzmann constant. Yes, so if we so this was the equation, and then if we, so this is total number of ion, and of course this is not composed, this may not be composed of the single species, so we need to, so to derive total number of ions, then you need to just summarize all the number density from all the species, which you can be written in this way. So this x is mass fraction of the some one ith element, and then you can divide by the mass number by the proton mass, and that's basically this is basically number number density. And this part is basically constant, so we can just define this mean weight of this ion. And let's say for the solar composition, you get this 1.3. So if we put this to this original equation, what we get is basically you can change this equation to this. So what we get is that this pressure is proportional to the density and also the temperature. So that's the gas equation of state for the ion gas pressure. And what else? So we have electrons. So the previous one was for ions. So we assume the fully ionized gases. And of course, the same can be done for the electrons, free electrons in the stars. And we can do the same exercise. So number of electrons will be, so assuming everything is ionized, then this is atomic number times. So this again, we sum over the whole elements. And then you can change this, change this number density in the similar way. And then we can define this average number of free electron per nucleon. And in the solar composition, it's like 1.2. So in this way, we can write this electron number density with just the density. So again, we get basically the similar, almost the same equation of state for the electron gas. So now we have the pressure for the gas and ion. Then we can, to get the total pressure from the gas, we can just simply add these two components, and that will lead to this simple equation of state for gas, which is proportional to the density and the temperature. So this was the gas pressure, and then let's imagine we think about the very high density region. So there's a gas here and governed by, let's say, this equation of state. We fix the temperature, and then let's say we imagine the system with higher density or smaller volume. So volume gets smaller and smaller. And at some point, you get close to, yes?
Excuse me, for the sun, in molecular weight, would be something like 1.6.
Yeah, something like that. Yeah.
It should be higher than.
Yes. So let me see. Yeah, I should have written that. So this is
for ions.
Yes. So yeah, 1 point. Basically.
In molecular weight for the sun, if we assume that the metal is fully ionized,
then it should be this, and you can calculate this. Sorry?
But if you put figures, you just take some like 1.6, no? As far as I remember.
So need it's yeah, you can calculate 1 point, well, yeah, should be something like that. I mean, some of you should have calculator. Yes. Yes, yes, yeah, that would be, yes. I found it. Let's, yeah, something like that, yes.
All of them are comparable, 1.2 if divided by 2.
Yes. Yeah. Yes, yes. So yeah, we can. So we can. So yeah, we can say this is almost 1.2, and then it's 1.22. So mu should be, roughly speaking. Thank you. Yes. So yeah, so we were talking about the ideal gas pressure, and as the volume gets smaller and smaller, and then the temperature basically gives you some distribution of velocity, and as the volume gets smaller, at some point we need to be careful about this Heisenberg's uncertainty principle. So we cannot specify the momentum and the volume where the particles are in more than, so we cannot specify this combination more than the Planck constant squared. No, sorry, the third. So that's so if we keep the temperature the same and then think about the smaller volume, then at some point we get close to this where this equation is gets equal, and that means the pressure pressure cannot be smaller than what you get from this value. So the pressure from some point, as the density gets higher and higher, will be governed by this Heisenberg uncertainty principle rather than the ideal gas pressure. Because ideal gas pressure, it doesn't care about this principle, and it just gives you, in the end, it can you can specify the velocity much less than this constraint. So at some point we get closer to this this regime. Then we also need to think about the Pauli exclusion principle. And yeah, so what we get. So let's let's see. So at some moment we get this regime. So delta V plus this pressure to the 3 will be, so the most extreme case will be this. And what we want to know to get the pressure is the number density of this with certain momentum. So we want to know this value, and yeah, dV dP, and basically so from this what we can get is, from this means basically dV, and this is the pressure in a certain volume in a pressure field, in the pressure, and so that basically become 4 pi p squared dP. That basically PR dP. That gives you the number of the I mean, this is the volume of the this D3 dpx. This is dpx dpy dpz. If you think about the kind of radius coordinate, then this can be written in this way, and this is now h to the third. So that means the number of electrons, which can be satisfying in this in this volume is say 4 pi. Let me show the result first. So yeah, so this is basically this volume, and in this volume, the maximum number of the states or electrons which can be in this volume is h to the 3. So how many electrons in this volume can be written in this way, because one electrons can occupy this in this condition. So the question is how many places you can have in this volume or in this space in this space, and that should be what is divided by h to the third. And then from the Pauli exclusion principle, there can be 2 electrons. So there's one spin up, spin down. So that there should be 2 in the same condition, in the same place. There can be 2 electrons which can be in this region. So that gives you the number density of electrons which can be which can be in this momentum, which can have momentum in this degeneracy pressure limit. So that gives you this number density in the momentum field, which can be satisfied in the field in the electron degeneracy limit. And let's say if there's a number of electrons there's some amount of electrons in the and then we can imagine you put the electron from the lower level. So basically we can. So there's the like some number density of electrons in a degenerated electron, and there's a pressure. We can imagine a situation you put from the bottom. You keep putting the electrons, and then at some energy, so that will be that this value will be this what's written there, and in some radius, all the electrons. So if you occupy electrons from the bottom, then you can keep putting everything, and then at some point you lose. All electron can be occupied, and then let's say that the pressure is Pf. We can imagine this kind of situation, and then the total number of electrons. If we have total number of electrons, then that can be written. That can be calculated in this way, and then this total, the highest pressure you have can be written in this way from the electron number density. So once we have this expression, we can again put this number density in this pressure equation. So previously, when we derived the equations of state for gas pressure, we used this Maxwellian density distribution. But now we got different expression for this number density. So instead of this one, we now put this one to get the new equation of state for the electron degenerate pressure. So then what we get is you simply put this one, and then you can easily calculate this pressure, and that will be given in this way. If you put everything in, then that will be written in this way, and these since those are all constants, assuming some electron mean molecular weight, then you basically this electron degeneracy pressure can be written. This is just proportional to the density, and that is not related to the temperature. So that this is the equation of state for the for the degenerate electron pressure. So, and then as the electron number density increases, this Pf will go up. So this was written like yes. So this is proportional to NE, number of electrons. You can imagine as the number of electrons increases, then this the maximum energy occupied by these electrons can just keep going up, and then of course the electron velocity of electron at this higher level will be just keep increasing. And at some point, these electrons will be relativistic. The velocity gets closer to the speed of light. So in that in that sense, in that case, this is no longer true. And yeah, as I said, yes, so this P, which we put there, needs to be, we need to think about the relativistic the momentum. Of course, you can put in this this expression to here and then try to integrate this, which you can do, but in a very simple way, you can just imagine this velocity became close to the speed of light, and then you can easily integrate this pressure expression, and that will give you this expression. So that leads to the in the relativistic case, the equation will state for the degenerate gas, electron gas will be like this. So this is still only related to the density, but the power is different. So previously, it was 5/3, but what we have for the electron, the relativistic case will be 4/3, and this difference is will be important. And then
maybe it's important to remind the listeners that the transition from non-relativistic case to relativistic case occurs at density something like 10⁶ grams. For example,
yeah,
this is much in the center of the sun, 100 grams per cubic centimeter. The white dwarfs already have the density so high that chapter 7.
yes,
So the 10⁶ is very easy to 1 million.
yeah.
$1 to your pockets, 1 million grams per cubic centimeter. It's okay. It's already starting to use it.
Thank you. So yeah, you can kind of get some idea by putting here m electron c, and then you can get the rough density. You can this effect will be important. Yes. So yeah, finally the radiation pressure. There's radiation. We were only now thinking about the electrons and the ions, and then there's radiation pressure. So another thing I should have said is we only thought about electron pressure, degenerate pressure, but of course ions, other non-electron protons, for example, can be degenerate. But that pressure will be very small because the mass of the mass of the electron is like about 2,000 times smaller than the ion, and that makes the degenerate pressure for the ions much smaller than those given by the electrons. So when we think about stars, we don't need to be. In the usual star we are discussing here, we don't need to think about the ion degenerate pressure. And yeah, finally we have the radiation pressure. That's of course in a relativistic particle, and we again have this pressure equation, and we can put this expression for the radiation, which is basically coming from the blackbody Planck function. And yeah, if you integrate, you can get this radiation pressure. Which is basically proportional to the temperature to the force. So that's the whole equation of states we got. So this is for gas pressure, which basically is proportional to the density and temperature. And then we got these two different kinds of degenerate pressure expression. One is for non-relativistic case, which goes 5/3. And then for the relativistic case, then this power will be changed. But both cases, temperature, they are not, they don't care about the temperature. And then radiation pressure will be temperature to the force. So based on these equation of states, we can think about some property of stars. And let's take this equation which we got in earlier in this lecture. This is the relation from the equation of motion. And we can, very roughly, we can do this on a star. Let's say there's a star of radius r and the mass of m. And so this, if you think about the entire star, this gradient will be, at the surface of the star, this the pressure will be 0. And then let's say this pressure at the center is Pc. And the radius at the surface of the star is the star radius, and the star radius at the center is 0. So this can be written in this way. And then let's say we take the mean mass and mean density and the mean radius for this side. Then you can write this this side in just mean values, and the mean density can be just written in m divided by volume. So if we do this, we can roughly get the pressure at the center of a star, which can be written this way. Let's imagine a star now supported by the degenerate pressure. So we now think about the electron degeneracy pressure, which should be proportional to the 5/3 as we saw. And then if let's imagine this center of the star is governed by the degenerate pressure. So we can put this to here, and then we can imagine just you can use the mean density again to get the idea. Then what you get from these relations is that the star, which is governed by the degenerate pressure, the mass of the star should be proportional to the radius to -3, and the mean density of the star should be proportional to the mass. So what does it mean? So let's imagine one star which is governed by this degenerate pressure, not the gas pressure like sun. So let's say this one example is like white dwarf. White dwarf is basically the equation of state can be governed by this degenerate pressure. So one white dwarf will be if the mass increases, then the radius of the white dwarf must go down with R to the -3, and then the density gets higher and higher with m to the squared as the mass increases. So as the mass of the white dwarf increases, the radius gets smaller and the density gets higher. And if you go very large masses, then basically density keep going up and up. At some moment, you can imagine the density become high enough to this electron degeneracy pressure to be relativistic, and so at some point, this was the central density we got in the previous slide. And then in the previous slide, we used just the electron degeneracy pressure. But at some point, the relativistic electrons will be dominating. And then equation of state will be written in a different form. So we can do the same exercise again. And yeah, using this mean density. And then what we get, if we use this expression, we get the constant mass for the relativistic, for our star, which is supported by free relativistic, the free relativistic electrons. So if we do the mathematics, then you get the mass from this equation of state, which can be written in this kind of way, and so that what basically mass will be just one value will be given, and because we did very simple. Very simplified analysis here, so the value we get in this way is much smaller than the actual value. So if we do the proper calculation, you get this maximum mass to be 5.8 divided by mu e squared, and if we put the this 2, which is roughly for the hydrogen-free cases, then you get this mass, which is called Chandrasekhar mass. So what does it mean? So if there's a white dwarf which is supported by the degenerate pressure, and as the density increases, at first the mass, the radius of this white dwarf will be decreased, and the density will be increased as the mass gets higher and higher. But at some point, the density become high enough for the white dwarf to have the relativistic degenerate electrons. So the equation of state gets this value, and that means there will be a maximum mass where the white dwarf can reach, and that mass is basically this what's called Chandrasekhar mass limit. So this Chandrasekhar mass limit, it can be basically derived by just basic equation we had. So this equation of motion and the equation of state for the electron degeneracy pressure. So just what we discussed now, just these two components will give you the maximum mass of the white dwarf, which is called Chandrasekhar mass limit. So basically, for this first part of the lecture, that was what we discussed. So we gave you the basic equations. Basically, there were 4 basic equations. Yeah, I didn't discuss the identity luminosity, but yeah, there's not only this energy radiation transport, but also convection. Other means of energy transport is important. And just based on these equations, we could derive the several timescale, dynamical and thermal and nuclear, and that had this kind of relation. Dynamical nuclear timescale is the longest timescale in a star, and that basically determines the lifetime of the star. And we also discussed the equation of states, which is basically the gas and the degenerate and relativistic degenerate case and radiation pressure. And just based on these two basic equations and the equation of states, we could derive the Chandrasekhar mass limit, which is the maximum mass which can be supported by the degenerate gas, and that was this value here. Basically, that's it for the first half of the lecture, and we have like 5 minutes or so for the questions.
So, I have small, just for listeners, maybe not that everyone is trained well with this science, in terms of science. And if you look at the Chandrasekhar mass, if you show that mass in slide mass, yes, you immediately find that this is not the calculation between Planckian mass divided by proton mass, right? Multiplied by the number of protons in the star. Once again, if you combine this, right? So we have a fundamental Planckian mass, right? Planckian mass is just HCOG, right? So what's written here is the Planckian mass divided by proton mass cubic multiplied by the number of protons. And this is the Chandrasekhar mass, actually, using a coefficient of order of 1. And a Planckian mass is a 10 to the 9 GeV, and the proton mass is 1 GeV, right? And you immediately find that this is the number of baryons which supports the Chandrasekhar mass of order of 10 to the 56. It's also well-known number. Or think about it. 10 to 56 baryons makes a star. And actually the sun is something like the same number.
Yeah.
So it is much easier to remember because it's a dimensional ratio of Planckian mass and proton mass times number of baryons.
Yeah, thank you very much. Yeah, so this was very simplified way to introduce these equations, and of course it's very hard to give this kind of lecture in 1.5 hours, and please, for more details you should refer to the standard textbook. That's for your reference. Any questions? Yes? That's famous textbooks.
So if there are no any questions, so let's